Hey there, welcome back. Today we're diving into the fascinating engine room of large language models.
Yeah, specifically looking at two key building blocks. The well-known transformer architecture.
The one everyone talks about.
Exactly. And also state space models, or SSMs, which are really gaining traction.
Right. Transformers, we know, are amazing for complex reasoning, finding those long-distance connections in text.
Definitely. But they can get, let's say, computationally heavy, especially as the text gets longer and longer.
And that's where SSMs shine, right? Their efficiency.
Precisely. They process sequences really fast,
Mm.
linearly, in fact. So great for long inputs. Historically, though, maybe not quite matching that deep reasoning power of transformers.
So you got these two powerful tools. One great for reasoning, one super efficient. Naturally, people want to combine them.
Get the best of both worlds, efficiency and reasoning power.
But it sounds like that's been a real challenge, like a major puzzle for AI researchers.
It really has. Despite the obvious potential, getting them to work together smoothly, it hasn't been straightforward.
And the core issue you're saying is how they understand the sequence itself, like fundamentally different views.
That's what the sources point to, yeah. How they handle sequence information, especially the idea of position.
Okay, and that brings us neatly to today's focus. We're unpacking a new paper from ArcGIF about a model called TransXSSM.
TransXSSM, yeah.
And they claim they've found a pretty clever solution to this integration problem by tackling that position issue head on.
That's the idea.
So our mission today is to dive into the sources you've shared, really understand this core challenge and what makes the proposed solution innovative.
Sounds good.
And the headline seems to be that TransXSSM manages to keep that transformer-level reasoning.
While getting much closer to SSM-level speed and efficiency.
Interesting. Okay, so let's start right there. Why is it so hard? What's the fundamental block when mixing transformers and SSMs?
Well, the core problem, as the paper lays out, is how they deal with positional information, where things are in the sequence. Transformers, they rely on that attention mechanism. But attention itself doesn't inherently know about order. You have to add that information back in.
Explicitly.
Explicitly, yes. And a really common, effective way is Rotary Position Embedding, or ROPE.
OP. Right.
Yeah, ROPE basically encodes where each token is using complex rotations. This lets the attention mechanism understand relative positions, how far apart words are, their order, crucial stuff.
Like knowing cat sat on mat is different from mat sat on cat. Position is key.
Exactly that. ROPE gives transformers that structure.
Yeah.
But SSMs, they work very differently.
How so?
They process sequences step by step, updating a kind of internal state. Information from earlier parts gets compressed into this evolving state.
So position is handled implicitly.
Implicitly, yeah. Through that recurrent update process, they don't have those explicit position-specific markers like ROPE that transformers use.
Ah, okay. So you stack some transformer layer, then an SSM layer, and they're speaking different positional languages.
Pretty much. That's what the paper calls positional encoding incompatibility. Imagine one system using map grid coordinates, the explicit ROPE.
Gotcha.
And the other using landmarks and travel time, the implicit SSM state. Passing information between them gets messy.
So information gets lost or kind of garbled in translation because the positional cues don't line up.
That's the core problem the researchers identified. Previous attempts at hybrid models often hit this wall.
Right.
If there's no unified way to understand position, those transformer layers, which really need those positional signals for complex reasoning and finding long-range links,
Their performance gets hurt.
exactly. Their effectiveness can be impaired when you mix them with SSM layers that just don't have that same explicit positional framework. This was the critical hurdle TransXSSM aimed to clear.
Okay, this is where it gets really interesting then. How did TransXSSM fix this? How do they get these two different beasts to agree on position?
The key innovation, the core technical piece, is something they call Unified Rotary Position Embedding, Unified ROPE.
Unified rope.
It's a novel approach. It takes the ROPE concept, originally just for transformers, remember?
Right.
And figures out how to make it work inside the SSM layers too.
How does that work technically? It sounds tricky.
Well, the elegance is in applying the same mathematical operation, that ROPE rotation, to the important signals in both types of layers.
Okay.
So in transformers, ROPE rotates the query and key vectors based on position. What TransXSSM does is apply the same kind of rotation to the SSM's internal signals that control how the state updates.
Ah.
Specifically, the paper mentions applying it to the C and B vectors in the SSM math, which they argue are analogous to the Q and K vectors in transformers in terms of how they influence the update.
So it's like giving the SSM layers the same kind of positional compass that the transformer layers are already using.
That's a really good analogy, yeah. By applying these consistent rotations everywhere to the self-attention inputs and the SSM state update signals unified ROPE, ensures that the positional information, how the model understands where things are,
Flows smoothly through the whole network.
Exactly. It flows continuously and coherently. The paper talks about achieving a spectrally continuous position representation. Basically, no more jarring resets or mismatches in positional understanding when you go from a transformer layer to an SSM layer or vice versa.
They're all on the same page positionally.
Precisely. Both parts interpret position shifts using the same unified mathematical approach.
That sounds like a really fundamental fix. But wait, the whole point of SSMs was speed, right? Does adding this ROPE step into the SSM layers slow them down? Does it negate that efficiency advantage?
That's a really important question, and according to the sources, the answer is no, it doesn't really hurt the efficiency.
Oh, okay. How?
Applying ROPE, even this unified version, is mathematically a pretty simple rotation. It happens before the main heavy lifting, before the main attention calculation, or the core SSM state computation.
So it's not adding a lot of computational overhead.
Right. It doesn't change the fundamental complexity of the SSM part, stays linear time, and it doesn't mess with the efficient algorithms used for inference. So you get this crucial positional coherence.
Without sacrificing the speed that makes SSMs attractive in the first place.
Exactly. Especially important when you're dealing with really long sequences.
Okay, that makes sense.
Yeah.
So unified ROPE is the glue.
Mm-hmm.
With that foundation, how did they actually build the TransSSM model? What's the overall architecture look like?
It follows a pretty standard deep network structure. Input gets processed through a stack of repeating modules. The innovation is really inside those modules and how they mix the layer types.
Right.
Each TransXSM module is itself a hybrid. The paper details the specific ratio they landed on after experiments. It's a 7-to-1 mix.
7-to-1, what does that mean?
It means within each module, you have 7 state space, or SS sublayers, followed by 1 self-attention, or SA sublayer. So a block of 7 SSM base layers, then 1 transformer-style attention layer.
And they stack these 7+1 modules.
That's right. Stack them up to build the full depth of the network.
Why that specific ratio, 7-to-1? Seems quite heavy on the SSM side.
Yeah, it's presented as an empirical trade-off they found worked well. The idea is the SSM layers handle the bulk of the sequence processing efficiently. That gives the model its speed and near-linear scaling with length.
Keeping it fast.
Keeping it fast. But then, that occasional self-attention layer, even though it's computationally more demanding...
It brings in that global view.
Exactly. It provides that crucial global context mixing and the strong relational reasoning across the entire sequence that pure SSMs can sometimes find challenging. So the ratio aims to balance that efficiency with the reasoning power.
Okay, so the 7.1 hybrid block is key. What else is important about the architecture?
Well, beyond just stacking those blocks, they highlight a few other design principles that are crucial for making it all work well.
Right.
First, principle 1 is just reiterating that unified rope. It's foundational. All the SS and SA layers in every module use the exact same unified rope. Consistency is key.
Got it. Unified rope everywhere.
Principle 2 is that hybrid module stacking, the 7.1 ratio we just talked about, strategically combining the strengths.
Makes sense.
Principle 3 is feature refinement. After each SS layer and each SA layer, they include standard feed-forward networks, FFNs.
Okay, standard practice.
Pretty standard, yeah. These FFNs process and enrich the features coming out of the SS or SA layer, adding complexity and learning capacity.
Right.
And finally, principle 4 is all about stability. Training these deep networks, especially with very long sequences, can be tricky. SSMs, for instance, can sometimes suffer from issues like state collapse. So to keep things stable during training, they use standard techniques, RMS normalization layers and residual skip connections. But they apply them rigorously around every single sublayer, both SS and SA, and it's following FFN.
So lots of normalization and skip connections to keep the training smooth.
Exactly. Particularly important in these deep hybrid models dealing with potentially massive sequence lengths.
Okay, so the theory sounds solid, unified rope fixing the core issue, and a carefully designed hybrid architecture. How did it actually perform? What did the experiments show?
The results they present look quite compelling, yeah. First, they tested unified ROPE on its own.
Just the encoding part.
Yeah, comparing it against other ways of handling position in pure SSMs and in simple hybrid setups. Unified ROPE consistently gave better results, specifically lower perplexity.
Lower perplexity means it's better at predicting the next word. Right. A better language model.
Exactly. So better modeling quality while staying efficient. They noted other methods often struggled or failed in the hybrid setting because of that incompatibility issue we discussed.
So unified ROPE itself seems to work. What about the full TransXSSM model?
Right. Then they compared the full model, specifically a 1.3 billion parameter version, against some big names.
Like Llama 3.
Yep, Llama 3 as a pure transformer benchmark, Mamba 2 as a leading pure SSM, and also Jamba, which is another hybrid architecture.
Then how did TransXSM stack up?
It showed some significant advantages both in speed and performance.
Okay, let's talk speed first.
Okay.
How much faster was it than, say, Llama 3?
At a pretty long sequence length, 4,000 tokens, they measured the 1.3B TransXSSM to be about 42.3% faster in training.
Wow, that's substantial.
And 29.5% faster in inference compared to the similar-sized Llama 3.
And compared to Mamba 2, the pure SSM.
Mamba 2 was still slightly faster, as you'd expect being pure SSM, but TransXSM closed that gap significantly while bringing in the attention layers for better reasoning. The sources show clear throughput wins over Llama 3 and Jamba, especially as sequences get longer.
Okay, faster's good. What about actual task performance? Understanding, reasoning?
That's where it gets really interesting. It performed very well across a whole range of standard downstream tasks. Benchmarks, testing comprehension, reasoning, common sense.
Consistently good.
Consistently competitive and often outperforming the baselines, yeah.
Were there any specific tasks that were particularly shown where that hybrid approach really seemed to pay off?
Yes, the paper highlights its strengths on tasks needing common sense reasoning and deeper contextual understanding. Benchmarks like HeliSwag, PIAQA, and they specifically call out Winogrand.
Winogrand. That's a tough one, right? Pronoun resolution needs careful reasoning.
Very tricky. And on Winogrand, the 1.3B TransXSSM significantly beat the 1.3B Llama 3 by almost 6.7 points, which is a big jump on that benchmark.
So nearly 7 points better on a core reasoning task.
Exactly. And they present that as strong evidence that the architecture, enabled by that unified position signal, is genuinely boosting reasoning capabilities compared to a pure transformer of the same size.
What about really long texts? Like finding that one specific fact buried deep in a document, the needle in a haystack test.
They tested that too, and TransXSSM showed strong performance there as well, successfully finding the needle across very long contexts, again outperforming some baselines.
And they link that back to unified ROPE.
They do. They suggest the consistent positional information provided by unified ROPE really helps with modeling deep context and maybe even performing multi-step reasoning over those long sequences.
Okay, so faster, good reasoning, handles long context. What about scaling? Does this advantage hold up if you build bigger versions?
That's a crucial finding they emphasized. Yes, it seems to scale really well.
Better than the others.
Apparently so. When they scaled the models from around 320 million parameters up to 1.3 billion, TransXSSM showed a bigger average performance jump across the benchmarks than Llama 3, Mamba 2, or Jamba did over the same scaling range.
So the gains actually increase as the model gets bigger relative to the others.
That's what the results suggest. It implies that the architectural principles, particularly that unified ROPE foundation, provide a really solid base for building larger, even more capable hybrid models. It seems to unlock more potential from adding parameters.
So if we put it all together, TransXSSM, with this unified ROPE idea at its heart, really does look like a significant step. It offers a practical way to build models that are efficient like SSMs, but reason well like transformers.
That certainly seems to be the conclusion from the research presented. By directly addressing that fundamental positional encoding mismatch, they've demonstrated a coherent, high-performing architecture that genuinely seems to blend the strengths of both approaches.
It's really amazing, isn't it, how solving a very specific, almost abstract technical problem, ensuring positional information flows continuously, can unlock such concrete benefits in speed, accuracy, and reasoning power.
It really underscores how much these fundamental architectural choices matter in pushing AI forward.
Absolutely. That was a really insightful deep dive into TransXSSM and why this unified ROPE concept is so important. It shows how critical these foundational details are, especially as we push towards models handling ever longer sequences and more complex tasks.
It definitely does. And, it makes you wonder if unifying positional encoding works so well here for transformers and SSMs, what other, maybe less obvious fundamental incompatibilities exist between different AI approaches?
That's a great point.
What other conceptual gaps are out there, and what kind of clever innovations might bridge those gaps in the future? Could lead to entirely new types of powerful models.
A really interesting thought to chew on. Definitely something for researchers and for us to keep thinking about as AI continues to evolve so rapidly. Well, we hope you found this exploration into the nuts and bolts of TransXSSM useful. If you're keen to learn more, definitely check out the paper on our site and keep an eye on this space. Thanks for joining us for this deep dive into TransXSSM.